Hello, everyone, and welcome to Jam Academy. In this lesson, we will talk about the rate of doing work. As a matter of fact, the objective of this lesson is to discuss the mathematical and conceptual implication of power. The word power is interesting because the word power is often the meaning of the word power in our daily conversations really vary greatly from the meaning of the word power in science. Power in our daily conversation is often equivalent to energy or force. When we say that someone is more powerful, we either mean that he has a lot of energy or he can exert a lot of force. But unfortunately, in physics, that is not the definition of the word power. Let me say that again. Power is not synonymous, it's not equivalent to force or energy. But keep that in mind that work is the work. Keep this in mind. Work is done when a force moves its point of application a certain distance. Let me say that again. Work is done when a force moves its point of application. That means that work can only be done provided there is motion. Hello everyone, and welcome to Jam Academy. In this lesson, which I'm very excited to present, we will talk about the meaning of the word power, the meaning and the conceptual implication of the rate of doing work. Now, the word power is often misconstrued by students because this word, the meaning of the word power in our daily conversation, actually differs from the meaning of that word in physics or science in general. In our daily conversations, if you talk to someone along the street, they will often imply that power implies energy or force. So when they say someone is more powerful, indirectly they're saying that he either has a lot of energy or he can exert a lot of force. But I'm here to submit to you that power is not synonymous to force or energy. As a matter of fact, power, energy, and force are totally different concepts, even though related to each other. The question is, what is work? Work is simply the transfer of energy when a force moves its point of application. Let me say that again. Work is the transfer of energy when a force moves its point of application. Now, in this particular definition of work, we do not mention time, which means that the work done by an object is independent of time, but depends on the size of the force, the direction in which the force is acting, and the magnitude of the displacement of the object. Now, let me ask you a question. Suppose that you have two students, Tom and Jerry. If Tom walks 2 meters under a minute and Jerry walks 2 meters over 5 minutes, which of these two students is more powerful? If we assume that Tom and Jerry have the same mass, well, I don't necessarily mean the cat and mouse, cartoon from Disney. Which of these two objects do more work? If they have the same mass, they will do the same amount of work, but one is obviously more powerful than the other. The student that does the same amount of work is in less time is considered in physics to be more powerful than the other student who does the same amount of work in more time. So the word power is used to imply the rate at which work is done. As a matter of fact, power is simply defined as the rate at which work is done. So the very first thing that I would like for us to talk about is average power. Average power. The average power of an object is simply defined as the average work done divided by the time it takes. Let me put it in a way that you can easily remember. If a certain amount of work delta W is done in a certain amount of time delta T, then the average power, the average rate at which that work is done is given by delta W divided by delta T. This formula, my friends, helps us to calculate the average power of a particular object. Understand that work is measured in joules, time is measured in seconds. This would mean that the unit of power or the dimensions of power is simply joules per seconds. This is equal to 1 watt. So the SI unit of the word power, of the physical quantity power, is simply the watt. We have an example right here. We have two students of the same mass, 50 kilograms. One takes about 20 minutes to run up a flight of stairs of about 200 meters of height, and the other student takes about 15 minutes to run up the same flight of stairs. So the question is, which of these two students is more powerful? Is it A or B? So for student A, let's calculate. If we draw a free body diagram on the student, the weight of the student acts vertically downwards. The normal force on the student acts vertically upwards. Now, it is the normal force that is responsible, to carry the student upwards. Now, assuming that the student is walking upward at a constant speed, we can clearly see that N is equal to mg. So the work done to lift the student from the ground to the top of the stairs, W, is going to be equal to mg multiplied by that distance traveled, h. This means that the power, the rate at which A does work, will be equal to mgh divided by delta TA, which is going to be equal to 50. Let me do this. This is equal to 50 kg multiplied by, I'm going to take G as 10 meters per square seconds, though it's 9.8. This is 200 meters. And all of this will be equal to 2,000 multiplied by 5, that will give us 10,000. 10,000 times 10, that is 100,000. So let me just make sure I verify this. We have 50 multiplied by 10 multiplied by 200. Yeah, that gives us 100,000 joules. So this is the amount of work that student A and student B does going up the flight of stairs. If you notice, A and B do the same amount of work, but which of these two students is more powerful? So let's calculate the average power for A. This is going to be equal to 100,000 joules divided by the total time, which is 20, multiplied by 60 seconds. And that will give us divided by 60 divided by 20. That will give us 83.3 watts. For student B, you have 100,000 divided by 15 times 60 seconds. This will give us 111.1 watts. So you can clearly see that student B is more powerful than student A. What does that mean? It simply means that student B does the same amount of work in a shorter time period. Let me say that again. Student B does the same amount of work in a shorter time period. So a more powerful object will do the same amount of work in a shorter time period. Now, it does not mean that he does more work. It simply implies he does the same amount of work in a shorter time period. Now, what about sometimes the rate at which work is done is not constant? When the rate at which work is done is not constant, we talk about instantaneous power. The instantaneous power is simply defined as the limit as delta t turns to 0 of delta w over delta t. This is going to be equal to dw all divided by dt. In other words, the instantaneous power P is equal to capital W all divided by dt. This definition right here gives us the instantaneous power of an object. Now, if you recall, work is the transfer of energy. This also implies that power can be defined as dE all divided by dt, where dE represents the transfer of energy. As a matter of fact, power is the rate at which energy is transferred. Now, there is a simple relationship between the rate at which an object does work and the net force acting on that object. Let us see what that relationship is. Keep in mind that by definition, W is defined as F. Well, delta W is defined as F multiplied by delta X. This would mean that average power is equal to delta W all divided by delta T. This will be equal to F multiplied by delta X divided by delta T. Now, delta X divided by delta T is just V. This would mean that the power of the rate at which an object does work is equal to the net force acting on that object multiplied by its speed. Multiplied by its speed. This is quite beautiful, and it's a formula that I urge you to remember. Now, we can actually use calculus to derive the rate at which the average rate at which energy is delivered onto a given system. What do I mean by that? From the above formula, the fact that P is equal to dW over dt implies that dW is equal to P dt. If we take the integrals of both sides from 0 to t, this is from 0 to W, we will end up with W equal to the integral from 0 to t of P dt. Now, this is another important equation that you might find interesting. Now, here's the deal. We know that P is equal to F multiplied by V. We know that P is equal to F multiplied by V. But what is F? F is equal to MA. So this is MA multiplied by V. We know that P is equal to FV, and V is equal to V naught plus AT. Assuming that the object starts from rest at the origin, this would mean that V is equal to A sub t. Hence, P will be equal to F multiplied by AT. But what is A? The acceleration A, from the fact that F is equal to ma, implies that A is equal to F divided by m. So this will be equal to F multiplied by F divided by m multiplied by t. And if that is the case, we can therefore see that the work done will be equal to the integral from 0 to t f squared over m t dt. Now, if f is constant and m is constant, we can actually take this out. So this is going to be equal to f squared divided by m, the integral from 0 to t dt, which will be equal to f squared over m t squared all divided by 2. T squared all divided by 2. Now, in other words, you can clearly see that W over T, which is equal to P, will be equal to F squared over M multiplied by T. This is the average power delivered by an object at a particular time T, provided that the average force acting on that object is equal to F. Now, this is a beautiful equation that I believe that you should be able to know how to apply. But before we go, remember that the unit of power is defined as the watt. So 1 watt is equal to 1 joules divided by 1 seconds. The joule is Newton meter all divided by seconds. 1 Newton is equal to 1 kilograms multiplied by meters divided by seconds squared. What that means is that 1 watt is equal to kilograms meters per square seconds multiplied by meters all divided by seconds. If you further simplify, this becomes kilograms meters squared per seconds cubed. So this is the equivalence of 1 watt. This is the equivalence of 1 watt. Now, the implication of this sentence is that the watt itself is a derived unit. And I have just expressed the watt in terms of the basic units. Now, I've often asked this in my tests or quizzes. Now, before I leave, the power has some very popular units that you will see in problems that we will solve in the future. And one of those very popular units is the horsepower. 1 horsepower is equivalent to 746 watts. 1 horsepower is equivalent to 746 watts. Another unit that you will meet, which is not the unit of power, but the unit of energy, is the kilowatt hour. Now, the kilowatt hour is a common unit used to measure the electrical energy transmitted by an electrical grid. So the kilowatt hour really is not the unit for power, but the unit for energy. Thank you so much, everyone. If you have any question, please do not hesitate to ask in the discussion forum below this video. Remain blessed, and bye-bye.